In this session, we're going to see how to solve rational inequalities. We're going to dive right in. We're given an inequality, x plus 12 over x minus 2 is greater than or equal to 0. Directions are solve the inequality, give the solution in interval notation. Now, as you may recall, a rational expression is an expression that has a polynomial numerator and a polynomial denominator. Lots of times variables floating around all over the place. Here's the deal. The numerator could either be positive or negative, depending on the value of x. The denominator could either be positive or negative, depending on the value of x. We can't piece these apart. We have to see how these signs interact. As you know, positive divided by negative would be negative. Positive divided by positive would be positive. So it's not a matter of whether the numerator or the denominator itself is positive, but again, how they interact. As with quadratic and other polynomial inequalities, we're going to have basically a three-step process. We are going to find zeros, pick test points, and write intervals. But now we have an additional consideration. When we find zeros, we're talking about zeros of the numerator, but we also want to know where the denominator zeroes out. Because remember, at a zero, the sign of an expression can change. So I'm going to draw a number line, label it x, because that's our variable of interest. And the numerator, x plus 12, would be 0 if x were negative 12. The denominator, x minus 2, would be 0 if x is equal to 2. So those two values define intervals, and what we want to do is pick test points in each of these intervals. To the left of negative 12, I'm thinking that a good test point might be, I don't know, x equals negative 15. Between negative 12 and 2, if ever I can use 0, I usually do. And to the right of 2, I don't know, 10. Any number to the right of 2. If you're not sure why that is, watch the video on polynomial inequalities or quadratic inequalities. Same principles apply. Here's a big difference though. While the numerator is 0 if x is equal to negative 12, the denominator being 0 at x equals 2 means it's undefined. And so I'm going to put an open circle on the number line at 2, indicating no matter what happens, I cannot put 2 into that expression. Now we have found zeros, we have picked test points. We're going to use the test points to figure out the sign of x plus 12 over x minus 2. I don't care about the actual number. What I care about is whether the output is positive or negative, because the inequality is supposed to consist of numbers that are greater than or equal to 0. So when x is negative 15, the numerator, x plus 12, is negative. The denominator, x minus 2, if x is negative 15, is negative. Negative divided by negative is positive. And so to the left of negative 12, this expression has a positive output. When x is 0, the numerator is positive, the denominator is negative, and positive divided by negative is going to be less than 0. And so we're going to say between negative 12 and 2, the expression has a negative output. When x is 10, 10 plus 12, the numerator is positive. The denominator, 10 minus 2, is positive. And positive divided by positive is, of course, positive. And so our expression evaluates to a positive output to the right of 2. Now we look back at our original inequality. We wanted values that made the expression greater than or equal to 0. Those are going to be the values that had a positive or a 0 output, keeping in mind that we can't include 2. So in interval notation, our answer is going to be negative infinity to negative 12 with a bracket, square bracket at 12, union 2 to infinity, because those numbers as inputs interplay in such a way that the expression is greater than or equal to 0. So that's the name of the game for what we're going to be looking at in this session. In our next example, same instructions, but our inequality is 1 over x minus 4 is greater than 3 over 2x plus 1. We might be tempted to multiply both sides by the least common denominator to clear the fractions, like we would with an equation. Don't ever do that with an inequality. I will tell you why. If the least common denominator is a variable expression, then sometimes it can be positive, and sometimes it can be negative. If I multiply an inequality by a positive value, then no big deal. If I multiply an inequality by a negative value, then the inequality symbol would have to reverse. Since we're talking about a variable expression that could be sometimes positive and sometimes negative, we wouldn't actually know whether to flip the inequality symbol or not. Now, whether you followed that or not, here's what I want you to get. Never clear fractions with rational expressions. I don't mean to holler at you, it's just kind of important. Okay, caveat. If you know for some reason that that rational denominator will never, ever, ever be negative, then you can do it. But it's just safer never to do it. Well, now I've made a mess of this stuff, so let me rewrite the original inequality. 1 over x minus 4 is greater than 3 over 2x plus 1. What made the last example straightforward was that we were comparing an expression's value to 0. So what I'm going to do, since I know I can't clear the fractions, I'm going to get both of the fractions on the same side. So I have 1 over x minus 4 minus 3 over 2x plus 1 is greater than 0. And that seems a little easier to stomach. Now here's what we're actually going to have to do. We need to combine these into one expression. In other words, we need to get common denominators. Not use it to clear anything, but use it to combine these two fractions. So, in the case of the first fraction, I need to multiply by 2x plus 1 over 2x plus 1. In the case of the second fraction, I need to multiply by x minus 4 over x minus 4 to get common denominators. And so I get 1 times 2x plus 1 minus 3 times the quantity of x minus 4 over the LCD, 2x plus 1 x minus 4, is greater than 0. I left this the way I did here for a reason. I'm not done with it yet, but I want to point out that this was subtraction once we moved everything on the same side, which means that when we deal with that x minus 4, we have to remember that we are distributing a negative 3, because that second numerator was actually negative 3, right? Well, when I simplify the numerator of this thing, I have 2x plus 1 minus 3x plus 12. And then the denominator, we said we were looking for the zeros of the numerator and the denominator, so we might as well leave it factored, 2x plus 1 over x minus 4. And then that's greater than 0. And then finally, collecting like terms, we get negative x plus 13 over 2x plus 1 over x minus 4. I'm going to draw a number line. I'm going to label it x because that's our variable. And I'm going to mark on the number line all of the values that will make either the numerator or the denominator equal to 0. So from the numerator, negative x plus 13, we have 13. From the denominator, x minus 4, we have a value of 4 that would make that 0. And 2x plus 1, we have a value of negative 1/2 that would make that equal to 0. Now, since the denominator can't be 0, I'm going to put open circles at negative 1/2 and 4 to remind myself, no matter what, I'm not going to include those values. At 13, the numerator is 0. That's what makes a fraction 0, and so I'm going to put a dot there. These are just kind of notes to myself. But now we need to pick test points in these intervals. Why don't you do that? Use a table to figure out positive versus negative and see if you can solve this inequality. Go ahead and pause the video and do that. So I picked values of negative 5, 0, 10, and 20 because those are in intervals defined by those points we put on the number line. Negative 5 in the numerator gives me a positive expression. In the denominator, negative 5, 2x plus 1 is going to be negative. X minus 4 is going to be negative. positive divided by negative times negative. That is positive divided by positive. That answer is going to be a positive output. If x is 0, the numerator, negative x plus 13, is positive. The denominator, 2x plus 1, is going to be positive if x is 0. X minus 4 is going to be negative if x is 0. Overall, the deal is I have an odd number of negative signs. Positive over positive times negative. This thing is going to be negative as an output there. When x is 10, the numerator, negative x plus 13, is going to be positive. The denominator has factors. 2x plus 1 will be positive if x is 10. X minus 4 will be positive if x is 10. Positive divided by positive times positive is positive. That was a lot of positives. If x is 20, then negative x plus 13 is negative for that numerator. In the denominator, 2x plus 1 will be positive. X minus 4 will be positive. Negative divided by positive times positive is negative. So see, what matters is how they all interplay together. Let me mark the number line that we have appropriately. So the outputs for this expression are going to be positive to the left of 1/2 and also in between 4 and 13. And negative between negative 1/2 and 4, and to the right of 13. Looking back at the inequality we have where it was being compared to 0, we wanted the expression to be greater than 0. That means positive. And so I want to write down intervals that gave us positive outputs. In other words, negative infinity to negative 1/2 with a parenthesis at 1/2 because it's a strict inequality. It didn't say it can be equal to. Even if it did say equal to, though, remember negative 1/2 came from the denominator. Can't include it. Anyway, negative infinity to negative 1/2 union with 4 to 13. Again, parentheses all around because it was a strict inequality. Next, we have z minus 5 over z squared plus 2z minus 8 is less than or equal to 0. I want you to pause the video and go ahead and solve this inequality. Okay, so the denominator, z squared plus 2z minus 8, factors into z plus 4 times z minus 2. And I have marked on a number line values that come from the numerator and denominator being 0. Z minus 5 is 0 when z is 5. Z minus 2 is 0 when z is 2. That's from the denominator. And z plus 4 is 0 when z is negative 4. That's also from the denominator. Remember, any value from the denominator will never be a part of our answer. Those are forbidden values. But a value from the numerator giving us 0 makes the expression 0. And so I have circles and a dot on my number line, which I have labeled z because that's our variable of interest. Now I'm going to pick test points in these intervals. And I'm going to use negative 5, 0, 4, and 10. I just need to pick numbers that are in intervals defined by those values that we have. And what I want for each of these inputs is whether the expression is positive or negative as an output. And then the last example, you may have noticed I was looking at the factors. And so I'm actually going to consider the factored form, z minus 5 over z plus 4 times z minus 2. I'm going to put negative 5, 0, 4, and 10, respectively, into this expression to see if each factor is positive or negative, so the output is positive or negative. Let me go ahead and whip through that. And if you haven't already done so, I leave it to you to confirm that values to the left of negative 4 will yield a negative output. Values between negative 4 and 2 will yield a positive output. Between 2 and 5, a negative output, and to the right of 5, a positive output. At this point, you're probably wondering, does it always alternate? I can tell you from experience, no, it doesn't. Do the math. Check it. So we wanted, if we compare to the original inequality, we wanted values that made the expression less than or equal to 0. That's negative or 0. So we're looking at values to the left of negative 4 and between 2 and 5, keeping in mind we never ever include a value that came from the denominator. And so in interval notation, our solution is going to be negative infinity to negative 4, a parenthesis at negative 4, because that came from the denominator. Union 2, which gets a parenthesis again from the denominator, comma 5, but 5 gets a square bracket because it came from the numerator. That means the expression is 0, and that counts for the non-strict inequality. Finally, we have x plus 2 over x minus 4 is greater than 1. This should be reminiscent of the second example. I'll just give you some guidance. We want to get everything on the same side with 0 on the other, and you'll need common denominators. So go ahead and work out this inequality. So I get x plus 2 over x minus 4 minus 1 is greater than 0. To get common denominators, I need to multiply that negative 1 by x minus 4 over x minus 4. And I have x plus 2 minus 1 times the quantity of x minus 4 over x minus 4 is greater than 0. Remembering to distribute that negative 1 in the numerator, I get x plus 2 minus x plus 4 all over x minus 4 is greater than 0. Let me collect my like terms. The x's kill each other. I have 6 over x minus 4 is greater than 0. Well, then I only have one number to put on the number line. That number is 4. I'm going to label it x because that's our variable. And so we just need a test point to the left of 4 and to the right of 4. I don't know, how about 0 and 10? We're going to play the same game as before. I'm going to put x as my input, 6 over x minus 4 as the output, and the inputs, 0 and 10. And I can see from that kind of analysis that to the left of 4, the expression has negative outputs. To the right of 4, the expression has positive outputs. Looking at the inequality that has 0 on one side, we wanted numbers that made the output greater than 0. Therefore, we're looking from 4 to infinity. Because it's a strict inequality, we're not going to include 4. Even if it was non-strict inequality, 4 came from the denominator, and so we never would have included it anyway. In any case, our answer is 4 to infinity with parentheses all around.